Okay, so to continue with our previous discussion on solving by Fourier series expansion of the linear wave equation, we are considering homogeneous equation with homogeneous boundary condition. So, we get a solution of this form as we discussed before. Now, some characteristics of the solution we can discuss now. So, one of these is, say, for example, if I have a situation, say suppose a string which is attached fixed at the two ends, and it was deformed to a initially a certain form as f(x), and then without any velocity, initial velocity is 0. That is what I wanted to say. See, suppose if g equal to 0, if g equal to 0, so what we have is, that is u t x 0 is 0. So, in that case what we have is u n x t, each of the solution will look like some constant c n into sine n pi x by L into cos n pi c t by L. So, n is varying from 1, 2, etc. Now, this is representing a standing wave with amplitude as given by this way, and frequency is pi c by L. So, and say for n equal to I can say this way, that x equal to 0, u n x t is 0, L by n, 2L by n, etc. up to L, u n is 0, u n x t is 0. So, that means displacement is 0 for x equal to 0, x equal to o n, which we call as the nodes for the nth harmonic. So, each of these we can call as the nth harmonic. Now, so this is a standing wave, represents now at a fixed t, so this is constant, this part is constant, and the displacement is measured by this way. So, this is the one we can call as the amplitude. Now, if we have say, so if we have say not g not equal to 0, so u n so each of this mode we can say as the u n x t is at a fixed t, at a fixed t, u n x t is constant, which is equal to c the whole c n cos what was that, n pi c t by L plus d n sine n pi c t by L. C t, this whole times constant times sine n pi x by L. So x range from say 0 to L, x is ranging from 0 to L. So this un is ranging. So n pi x by L, n pi x by L range from 0 to n pi. So this is the n times the half period of sine, n times the, so which is n times half period of sine. So that means say n equal to 0, that is the usual position. N equal to 1, you have a situation. If you have n equal to 1, so if you have a situation like this way, n equal to 2, you have this is x L, like that, right? So this is the u. So this is the form of different form or different shape the vibrating string will assume as the time progresses. So it can have different mode of vibration, and these are the form or shape sine curves will take. So depending on that harmonics, we have number of notes, how many it will within the interval can be talked about. Now the same idea or same technique will illustrate for another important type of equation, which is the elliptic type of equations, and is also sometime it's very important. This like Laplace equation or Poisson equations, which provides the heat or heat distribution or electric potential or force potential. Any potential equation is governed by either a Laplace equation or Poisson equation, and these equations, these type of problems are purely boundary value, because this all the boundary conditions are given. So for example, you have a sphere whose temperature on the surface of the outer surface of the sphere, we know the temperature distribution, and there is no heat source, and if you want to find out the temperature at any point within the sphere, metal sphere, so that is governed by the equation, the Laplace equation. So let us first talk about a solution of the Laplace equation. So let us take u is the one. So now we talk about elliptic PDE, and say this is the Laplace equation. If it is a homogeneous, so first we restrict to homogeneous equation, del to u equal to 0, and in D certain domain, and u is prescribed on B, the boundary of D. Boundary of the domain D. So our task is, what is u xy to obtain in D, inside the D. Now first let us talk a simple situation. So D, let us take a rectangle. D is given by A, or instead of A, let us take 0. So origin is the first point, 0 less than x less than A, 0 less than y less than B. This is the rectangle, and so we have the condition BC, boundary conditions are prescribed. One condition should be homogeneous condition in one variable for our simple way of solving. So 0 to y, say, and that means this is for 0 less than y less than b. Another BC is about the x, that can be non-homogeneous. That has to be non-homogeneous. Otherwise, if you have a homogeneous equation, homogeneous boundary condition, you will get a zero solution. That is not possible to have a non-zero solution. So, this can be a homogeneous boundary condition. So, this is for 0 less than x less than a. So, basically what we are looking for, we have a domain, say like this way, this is x, this is y, and we have a domain this. So, this is a b, this is a0 and this is b0. So, the solution to be find out inside the domain D, this is we are calling as the domain D, and the four sides are the boundary, and U is prescribed on the boundaries. So, need to find out U at the interior point. Now, one condition, as I said, is that the one of the boundary condition should be homogeneous BC with respect to one variable. Without that also is possible, but there are some tricks to be applied. So, for the time being, we assume that we have a situation given by this way, elliptic PDE given by this way, is also referred as a temperature distribution equation. Say certain slab of certain heated to a certain temperature, boundary are maintained with a fixed temperature and heat diffusion is in progress. So, at any position the temperature inside the domain is governed by the Laplace equation. So, we look for a solution u x y as x x y y. Now, if I substitute, I get x double dash by x equal to minus y double dash by y. Again, this has to be negative less than 0. You can challenge this and you will find that it will be a non-trivial solution. So, for the sake of non-trivial solution, we should have it is negative. And if I solve x double dash plus lambda square x equal to 0, because if we have homogeneous condition with respect to x, then we should take up the solving the x, capital X. That means the function with respect to x, and if we have the condition, homogeneous condition is given with respect to y. So, then we have to take the condition, first solve this y. So, if I solve this, so what I get is lambda n. The same way, lambda n square is comes out to be n square pi square by s square, and corresponding x n is sin n pi x by a. So, this is the eigenvalue and eigenfunctions respectively. So, with that we find out the y n double dash minus n square pi square by s square y n equal to 0. So, we get y n, this is y n y is comes out to be b n e to the power, if I do this after doing some manipulation, n pi and using the boundary conditions. So if I use the boundary condition that see, it will be Bn, why I am writing Bn, okay, Bn if we write, so Bn n pi and a by y plus say Cn e to the power minus n pi a by y, and what we have is y, not y, capital Y, y n, because we have homogeneous condition which is at B. So y n b is 0. This implies I get a relation between Bn and Cn. So using this I can write as capital Y. So capital Y n y can be written as some constant, say let us call some Bn bar and Cn bar, so let us call Bn e to the power n pi minus n pi y by a into e to the power n pi b by a minus e to the power n pi y by a into e to the power n pi b by a minus n pi b by a. So this gives you Bn sine hyperbolic n pi by a b minus y. So now we have used both, only one condition is left. Both condition for x is used and one homogeneous condition for y is used. So we can write now uxy in terms of a single constant in this form. Let us call that dn, because xn is also having a constant. So see bn and that constant, because all this un will be multiplied with the constant. So combinedly I can consider only one constant. So dn sine n pi x by a into sine hyperbolic n pi by a into b minus y. Now which condition we to use or left is ux0 equal to fx. Now as usual again we use the condition for orthogonality of the eigen function. So one can do this way, that dn and if I multiply by, so x equal to 0, y equal to 0, if I put, so dn sine hyperbolic n pi by a into b, this becomes this is 2 by a, so 2 by a 0 to a fx sine n pi x by a dx. So this gives you the solution, requisite solution. So from here we get the dn, all the constant dn's are obtained. So this gives the series solution. So this is from the 1 to infinity in terms of the eigenfunctions. So we have discussed so far all the particular type of equations, parabolic, hyperbolic, and now this is the elliptic, and these are all very important in the context of, say, transport equation that is covered by the parabolic equation, that is without any dissipation, only rather which is only by dissipation. So that is the parabolic PDE, only which is governed by the diffusion mechanism. Another is that convection mechanism without any diffusion occurrence, that is the hyperbolic one, and this is the elliptic, which governs say any potential equations or heat distribution in a steady state and all these things. Now, some cases when we have a non-homogeneous situation, we have already discussed one situations. So, non-homogeneous means where we have to expand the non-homogeneous term in a form of a series expansion, eigen function expansion technique. That is the thing we have utilized. So, for example, even the Poisson equations can also be solved by the same method. So, Poisson equation means what we have is, now one thing to remember is that the elliptic equation cannot have a infinite domain, in the sense that it is a boundary value problem, because x and y, they are corresponding to or r theta, whichever way. So, the space variable, so there is no time derivative involves. So, the space variables which will have a finite range, but one can have in several situations also infinite, semi-infinite or infinite cases. So, in this case the technique whatever we have discussed here is no longer applicable or straight away cannot be applied. Now, consider this Poisson equation means when we have non-homogeneous situation. So, that means you have a situation like this way. So, if we have a situation like this, so this is a non-homogeneous equation. Non-homogeneous, and we can have a boundary condition, say u equal to maybe gxy in B, B, which is the boundary non-homogeneous in D. So, B is the boundary of D. D is bounded by B. So, as the previous one we discussed, there what we required is the boundary condition for one variable must have to be homogeneous. So, now we have, if we want to apply the previous case, so we have to do some trick. The trick will be that if I write that u as some function v plus w, so w some known function, a simple form should be chosen in such a way that w takes care of the non-homogeneous fxy, and also w makes the v to assume homogeneous boundary condition. Now, say we have a equation like del 2 u equal to minus 2, for example, which is a Poisson equation, del 2 u equal to minus 2, and in say 0 less than x less than a and 0 less than y less than b, and u equal to 0 on the boundary. Rectangular boundary in this case. So, it is a Poisson equation and it is a rectangular boundary, but homogeneous. Now, it is a non-homogeneous equation, homogeneous boundary condition, so non-zero solution is possible. Now, if I write u equal to some v plus w, w to be determined. Now, w should be in such a way that del 2 w equal to minus 2 and can be obtained very easily. So, if I choose, if I do not want to disturb the non-homogeneous boundary condition for y. So, if I choose, say for example, w equal to, for example, if I choose say minus x square. So, if I choose w equal to minus x square, that satisfies. So, del to w equal to minus 2, that is happening. But what is not happening is that the boundary condition. So, at x equal to a, this is becoming a square, minus a square. So, that means it was homogeneous. Now, for v, this is becoming a non-homogeneous. So, this way it does not work. It may not, it won't be a good choice if I simply take w equal to minus x square. So, one way to remedy is that if I choose, say, let w equal to ax minus x square. Now, if I would have taken a only or a square minus x square, then the problem was at x equal to 0, it will be again a non-homogeneous. But if I now take this one, so what will happen is w equal to 0 at both x equal to 0 as well as x equal to a, and del to w equal to minus 2. So, both the requirement are satisfied. So, instead of choosing these, I choose w equal to ax minus x square. So, now our u equal to v plus ax minus x square, and this v is now satisfying all the conditions, that is v equal to del to v equal to 0 in domain D, and v equal to 0 on for x equal to 0 and a in the entire domain of y, but v is v x 0 is x ax minus x square equal to v x b. So, we have non-homogeneous boundary condition for y x b. So, now this can be solved the way we have discussed before. So, these tricks are possible for solving the situation where we have a Poisson equation, but many cases we may not have a simple type as we have here. We may not be that lucky if fxy is a complicated one. So, but in many simple situations, so our requirement should be, or our objective will be, that if we have a Poisson equations, so that has to be reduced to a homogeneous equation by a substitution like this way, by using a simple function x, and a boundary condition with respect to one of the variable must be homogeneous. Otherwise, then the situation creates a difficulty. But in many complicated or practically applicable problems, we may not have those readily available solutions. So, in that case, we have to rely on the integral transform techniques, which will be discussed next. And prior to that, what we will be doing is the Green's function technique. So, this will be our next topic. So, in the Green's function technique, what we do is we reduce this BVP, a boundary value problem, we reduce to a integral equation. So, this is the objective for the Green's function technique. But again, the Green's function technique also has several drawbacks and all, because the integral equations is also another complicated. So subsequently we will talk about the integral transforms, and the most useful things for all the complicated situation is the numerical methods. So that we will discuss in the subsequent lectures. Thank you for today.